Electrons have spin. So, whenever we talk of electron eigenfunction, we have to talk in terms of spin as well. So, let us say that the eigenfunction of this H of 1, although H need not contain spin, H may be only a function of space coordinates, electrons still have to be attached on that space wave function with a spin alpha or beta. So, we will call these orbitals or spin orbitals. So, let us say this is the eigenvalue equation of the one particle operator. So, now please note a symbol that I am using chi. So, these chi's are what I now call spin orbital. So, we will try to make sure that we use this symbol whenever we have spin orbital. What is a spin orbital? Again I repeat, it is a one electron function containing the space coordinates and the spin coordinates. So, let me write it very specifically. So, H again depends on only R1, 3-dimensional R1, which can be R1 theta 1 phi 1 or x1 y1 z1, whatever coordinate system. However, chi I now depends on R1 of course, but also on the spin coordinates, which I now call omega. So, my spin coordinates are R and omega. So, this will be energy of chi I R1 omega 1. So, this is the long form of this equation. When I am writing the short form 1, remember 1 refers to the coordinates of the electron 1 and whatever coordinates are required. So, this is space only, this can be spin. This can also have a spin in a many particle problem, or in general also even for hydrogen atom when there are other effects like relativistic effects and so on. We are not worrying about those effects in the Hamiltonian. So, our entire discussion is actually on non-relativistic quantum mechanics here. So, the operator itself does not have a spin. However, the wave function of the electron must have a spin, and we are calling the spin coordinate as omega 1. Remember, the orbital spin, the spin part is not omega 1. The coordinates are only omega 1, just like the coordinates here are r. The functions which depend on omega will be called the spin functions. And these two, there are two such functions. One is an alpha function with a half up spin, another is a beta function with a down spin. Okay. So, if I can solve the regular space part, all I have to do is to attach the alpha part or the beta part to generate the chi. Okay. So, let us say what are the chi's. So, chi's are these chi's which are called spin orbitals. So, the spin orbitals chi I are now product of the space part and spin part. Okay. Again, we have to be very careful about these symbols as much as possible from now on. So, let me write down a chi I of r omega. Note that this was r1 omega 1, I am writing generally r omega. So, it can be r1, r2, whatever. So, this has to be a product of a space part alone, and I am calling this phi, let us say from phi k r, and a spin part which is either alpha or beta. So, it will make it very clear to you that what I mean by the spin coordinate omega. The functions are actually alpha and beta, as you have learned, okay, up spin and down spin, but those functions also depend on a coordinate, just like your 1s orbital in hydrogen atom depends on r theta phi. So, those coordinates are what I am calling omega. So, omega is not the actual function, the function is either alpha or beta. So, for every space part, how many spin orbitals? This is an orbital, this is a spin orbital. So, for every orbital, I can generate 2 spin orbitals, correct, trivially by attaching 2 spin functions, and there are only 2 spin functions. alpha omega, beta omega. There are many space parts, but spin functions are only 2. So, for every space function, I can generate 2 spin orbitals. So, these are called spin orbitals, just as these are, because they are 1 electron functions, but functions of space and spin coordinates, and these just the phi k of r we will call orbital. So, please make sure that the symbols you understand. When I say orbital, that means it is just the space part. Okay. When I say spin orbital, it has the space part multiplied by the spin part, and this is just the spin function. So, you do not have to bother about this. Okay. The space and spin, there is no coupling in my Hamiltonian. Okay. We can't do that if the space spin orbital coupling is there. There is a coupling, what is called spin orbit coupling, which is not there in the Hamiltonian. So, that is what I know. I first said that the Hamiltonian depends only on the space part. So, the spin is just attached, there is no coupling. It has to be in the wave function because electrons have spin, but those 2 spins are uncoupled with the space part. So, they can, just like a non-interacting Hamiltonian, we are attaching the eigenfunction as a product. So, here we simply attach as a product because there is no coupling. So, otherwise you are right, they actually have a separate basis called the spinor basis, which are more complicated basis for those kind of couplings. Okay, and those are dealt in a different level. Okay, and quantum mechanics, but our quantum mechanics is non-relativistic. So, the spin simply gets attached. So, spin is very simple to a 1 particle part, but when you generate many particles, you will see that if there are complications even here. But as of now, for 1 particle, it is just trivial. You simply attach it. So, that is the reason I said orbital is a 3-dimensional quantity, spin orbital is a 4-dimensional quantity, because this r has 3 and omega adds to a 1 dimension. So, you have total 4 dimensions for the spin orbitals. Okay. So, let us assume that we know how to solve this 1 particle problem for a non-interacting Hamiltonian. Then we said that the eigenfunction of these must be a product of these spin orbitals. But now we know that this product must be antisymmetrized product, right? This must be an antisymmetrized product. So, we will see how to do that, because we have already written that they must be antisymmetrized product. So, let us assume that we have solved this problem and we have got set of spin orbitals chi1, chi2, chi3, etc. Okay, which are basically nothing but set of space orbitals with spin attached. Okay, and each of them has an eigenvalue epsilon 1, epsilon 2, epsilon 3, and so on. Quite trivially, these space parts can be solved separately, in which case, of course, the eigenvalues will be equal. Like if I have these two have same space part, the eigenvalues of E1 and E2 will be equal, and so on. But in general, I am writing this as E1, E2, E3. Right now, you do not have to bother which are equal and not equal. Okay, many of them may be equal. So, I have a set of spin orbitals for this 1 particle problem and a set of eigenvalues of this 1 particle problem. Then I want to construct the wave function for the 2 particle problem. So, this is the wave function. Remember, this wave function is no longer orbital, because orbital has to be 1 particle, spin orbital or orbital has to be 1 particle. So, it is a 2 particle function. I am just calling it wave function now, which should be the eigenfunction of this Hamiltonian. What does our theorem says? What does our theorem say? The theorem says that this psi of 1, 2 must be an antisymmetrized product of the eigenfunctions of the 1 particle problem, right? So, for example, psi of 2, 1, 2 can be a product of any sets of chi1. Now, the only catch is that they must be antisymmetrized product. So, let us assume what we can, let us say I put this both the electrons in chi1 to start with, let us say. So, let us analyze this function, where I write psi of 1, 2 as a product of 2 1 particle functions, and both of them are in chi1 spin orbital. Now, let us analyze this. Is it antisymmetric? What is the answer? No. All of you are convinced? That is, if I interchange 1 and 2, they become identical. So it is not antisymmetric. It is actually a symmetric function, and this can be a good, a valid non-interacting Bose eigenfunction for Bose particles, but not for, so not for the electrons. So what can I do now? So let us analyze another function. I put chi1 1 and chi2 2. Since I can't put in the same, so let us write this as a chi1 1 into chi2 2. And I ask the same question now. Now I know that already that one spin orbital cannot have 2 electrons, correct, because I can't antisymmetrize. In fact, you already know that that is Pauli exclusion principle. So what I just now showed is basically the Pauli exclusion principle. Because of the antisymmetry, Pauli exclusion principle is valid. But now what about putting one electron in one spin orbital and another in another spin orbital? So for example, chi1 can be space part phi 1 into alpha, chi2 can be another same space part phi 1 times beta, or different space part with a different spin part, does not matter. Now this is clearly possible, and we know that, for example, helium atom, we have one is alpha, one is beta, right. So this is clearly possible. So I can obviously put 2 electrons, one in chi1, one in chi2. But is it antisymmetric? Answer again is no. So even though it is possible and we know that we can do it, clearly it is not antisymmetric. So then the question comes, how do I antisymmetrize? If you note the next wave function, so let us analyze this wave function now, where I put chi1 1 and chi2 2, and then subtract from it chi1 of 2, chi2 of 1. Okay, which means I have put the 2 electrons, one in chi1 and one in chi2, except that the first electron here was in chi1, the second electron here was chi2. I am now mixing it up, the second electron in chi1, first electron in chi2, and I put deliberately a minus sign. Is it antisymmetric? The answer clearly is yes, because if I make interchange of 1 2, this part becomes this part becomes this part, and because of the sign, one negative sign, they become antisymmetric. So now in this case, this is a valid wave function. Right now I am not worried about the normalization. Remember that it may not be normalized unity, so that part I am not worried, well, that can be trivially done, but it is a valid wave function. So it is possible to construct a valid wave function of a 2 electrons by using at least 2 spin orbitals. Okay, only 2 spin orbitals, I should say, not even at least. Okay, 2 spin orbitals, I can construct a product. If I have more spin orbitals, I can construct more products. Okay, many more than one product, but at least 2 are required. One is not enough, because the one I cannot antisymmetrize. Note that you might have said, why don't you do the same exercise here? Write chi1 1, chi2, chi1 2, and then write it again minus. But you will see they are identical, so it will become 0. Right? Had I written this chi1 1, chi1 2, and interchange 1 and 2, subtracted, it would have become 0. So there is no way, and that is the Pauli principle. But at least 2 different spin orbitals I can antisymmetrize by properly combining. With a negative sign, I interchange 1 and 2 with the negative signs, and that becomes an antisymmetry. Antisymmetry. Otherwise, you will not get antisymmetry. If it is plus, it is not antisymmetry. It will become symmetric function, again Bose function. Because we have already said that our electronic functions must be antisymmetric. So it is true to antisymmetry. So there is a tremendous significance. In fact, if you put plus, then it will go to a Bose function. It will not be electrons. Right? You understand? Because then if I put 2 1, then this will become this will become this, they are plus. So it is the same function. So minus is extremely important. Correct? So let us analyze how do I write this function in a manner which is generalizable to a larger n particle problem. Right now we are discussing only 2 particle problem. Eventually you have to write for n particle problem for any pair. Before you do that, let's analyze these function.